And today I'm going to tell you about a project called Exposure Notifications Private Analytics. This project was quite exciting for me, first because it was an application of some of the advanced cryptographic techniques that I usually work on. And second, because it was a cross-company collaboration, which is usually something rare that doesn't happen quite often. So in a recent study, researchers from University of Washington and researchers from the Washington State Health Authority estimated that the use of the Exposure Notifications Express application in the state of Washington between November 2020 and March 2021 resulted in averting approximately 6,000 cases of COVID-19 infections. So in this talk, I'm going to tell you about the system that produced the data which these researchers were using for their study. So for the rest of the presentation, I'm going to introduce to you what is exposure notifications, which was a system that was offered both by Google and Apple on their mobile devices. I will introduce the need for private analytics and why we decided to develop the exposure notifications private analytics system. I will outline what was the design, as well as the instantiation and the deployment of the system. And then I will conclude with some discussions of the challenges that we saw in the real deployment of this system, and some thoughts and ideas of how we should think about these points when we develop future systems that rely on similar techniques. So let's start with overviewing what is exposure notifications. Exposure notifications is a digital solution which was jointly developed by Google and Apple in order to help regular users in the COVID-19 pandemic. In particular, it was providing a privacy-preserving proximity detection in order to help users become aware of possible exposures to the COVID-19 virus. So I will walk you through an example and try to explain how the exposure notification system works. So the basic underlying idea under this system is that each mobile device will broadcast constantly non-identifiable Bluetooth beacons. You can think of these Bluetooth beacons as random numbers which will change fairly frequently. All right. Hopefully all the technical difficulties will end with this. So each mobile phone will be broadcasting these non-identifiable Bluetooth beacons, which will be changing fairly frequently. For example, you can think of this as every 15 minutes. And these beacons are basically random numbers that each device will be broadcasting. And then at the same time, all devices that are in the vicinity will be listening and will be recording the beacons that they hear. So for example, if Alice and Bob are having a conversation on a bench in the park, their phones will be broadcasting their respective beacons, and the phone of the other person will be recording what it's hearing. So if later Bob tests positively for COVID-19, he will be given the option to consent and have his phone upload the cryptographic keys that were used to generate the beacons that his phone has broadcasted for the last 14 days to a centralized health authority server. And in particular, the period 14 days was chosen because this was supposed to be the period for infectiousness of the virus. So now Alice continues with her daily activities unaware of the fact that Bob has tested positive for the virus. However, her phone is regularly downloading the database of this health server that includes the keys of all users who have reported that they have been infected with the virus. And I want to kind of emphasize that these keys that are uploaded to the server are unlinkable to the actual devices or the actual users who decided to report. So Alice's phone will download the database with the new keys which Bob reported. It will run locally a matching algorithm between the downloaded keys and the beacons that Alice's phone had collected, in particular during her conversation with Bob in the park. And based on this, her phone will send her a notification about possible exposure to the virus, together with a message with directions provided by the respective health authority. So in this way, Alice will become aware and she might choose to follow the directions from the health authority. So exposure notifications was designed with very strong privacy principles in mind. First, this was an opt-in solution. So every user had to actively consent before their device starts to broadcast any of the beacons or start any of the scanning for beacons sent by other devices. Also, there was a separate consent when a user tests positive and decides to upload their keys in order to notify the other people who might have been exposed to the virus. There was a separate consent that they have to agree to. As I already mentioned, all of these random beacons are completely non-identifiable and non-linkable, and any user that never reports, decides never to report an infection or never becomes infectious, cannot be linked to any of their random beacons that their device has sent around. And also, when a user reports their keys, all the matching happens only locally on devices. There is no collection of a centralized graph or no central server that is able to detect the matching between reported keys and the broadcasted random beacons. So this was very good for user privacy, right? The only information that the exposure notification system reveals is to a user themselves, and this is the information whether they might have been in proximity to other users who have tested positive for the virus. However, these strong privacy guarantees also prevented health authorities of being able to find out any useful epidemiology information about the spread of the disease or about the effectiveness of the system. So the question that we were trying to answer is if there is a way to help health authorities find out and evaluate the effectiveness of the exposure notification system, but in a way that abides with the strong privacy principles that were used to design exposure notifications itself. So some interesting questions that health authorities were interested to learn about was, for example, to find out how many notifications are displayed based on the fact that somebody had reported a positive test for COVID-19, or maybe how many of the people who receive notifications end up testing positively later for the virus. The local matching that I told you that happens on each device, which matches between the reported keys and the beacons that the device has collected, also utilizes a threshold to decide whether an exposure notification should be displayed to the user. And this threshold depends on parameters that are determined by the health authorities, and it was useful for them to be able to fine-tune these parameters, and in particular to find out what will happen if they raise the risk threshold, for example, how many more people would receive notifications, or if they lower the risk threshold, how many people who actually test positive for the virus will not receive notifications. So in order to answer these types of questions for health authorities, there was a need to come up with a way to collect some useful metrics from the exposure notification system while upholding the privacy principles that we had established for exposure notifications. So the goal for the exposure notifications private analytics systems that we wanted to achieve was first to enable the collection of aggregate metrics and only aggregate metrics. In particular, we wanted to guarantee that no individual contributions will be available or could be learned by any participant in the system. We also wanted to guarantee that the only party that would have access even to the aggregate metrics will be the respective health authority. So Apple and Google do not have access even to the aggregate metrics in this system. We also wanted to guarantee robustness in the following sense. We want to prevent a single user to be able to skew disproportionately the result of these metrics. So we wanted to bound the effect that a single user might have in order to guarantee the usefulness of these metrics for the health authorities. And last but not least, it was important to have a common solution that works across the iOS and Android devices so that health authorities can obtain metrics across the whole population. I just want to make a note that everything that I'll be describing for the rest of the talk applies only for the exposure notifications express application, which was a variant of exposure notifications that Google and Apple developed, and it was mostly deployed in the US. So now that we know what is exposure notifications and why did we want to introduce private analytics in this system, let's look at how we actually designed this private analytics system. As I mentioned to you, we wanted to have a solution that is based on well-recognized work that will be well known to all participants and will be accepted for its privacy and security guarantees. And that's why we chose to use the paper introduced by Henry Corrigan Gibbs and Dan Bonnet in 2017, which proposed PRIO, a private, robust, and scalable computation of aggregate statistics. We chose to use this well-established paper rather than come up with new solutions because we thought this matches exactly our requirements. In particular, the interesting properties that this system introduced was that this was a multi-party aggregation solution that distributes the trust in the system across several different parties. It guarantees that individual contributions will be protected and only aggregate metrics will be revealed at the end of the computation. The proposed solution had some interesting properties that allowed it to be easily extended to achieve also differential privacy for the final outputs. And last but not least, this solution provided protection against malicious users. And it was basically guaranteeing that the only thing a malicious user who tries to mess up with the system can do is essentially lie about their own input. Another interesting point about this design was that it had been used previously in the context of privacy-preserving telemetry aggregation by Firefox. So we had some example where this solution had worked out. All right, so let's look at the architecture that underlies the PRIO system. This architecture relies on two non-colluding servers. And what non-colluding means here is that we need to choose two parties that will be independent and will be trusted not to put together the data that they receive during the execution of the protocol in order to compromise user privacy. Later in the talk, I will tell you which parties we use to instantiate this in the US. So a contribution, a user device prepares the contribution for this private metrics by computing a binary vector where for each metric that we are computing, we are partitioning the range of possible values in a few buckets. And then the user device increments only the bucket that corresponds to the actual value for this particular metric that they are contributing to. Once the input is prepared as this binary vector, what the device does is that it splits this vector in two cryptographic shares. And the properties of these cryptographic shares are as follows. If you look at only one of the shares in isolation, this share is indistinguishable from a random number. Only when you put together the two shares, you will be able to recover information about the original input that was shared between these two cryptographic shares. And in particular, it is easy to see how you can generate these shares by just sampling one random vector that will be sent to one of the servers and then computing the other share for the second server by subtracting from the input binary vector, the first random vector. In addition to the secret shares, the mobile device also computes what is called a cryptographic zero-knowledge proof. And this proof aims to convince the two servers that the user has sent a valid input, where valid here means is that the input is a binary vector. And while I don't have time to explain the details of how this zero-knowledge proof works, at a high level, we can prove that a vector is binary if we can show that each of its entries satisfy a polynomial that has roots 0 and 1. So now that all mobile devices send these cryptographic shares of their inputs and the proofs of correctness to the two servers, the two servers will first jointly verify the correctness of the proofs and will filter only the inputs that satisfy these proofs. And here I want to make the point that these zero-knowledge proofs are a special type of proofs that benefit from the fact that we have two non-colluding verifiers and achieve much better efficiency compared to zero-knowledge proofs that have to work with a single verifier. So once these proof checks are completed, the two aggregation servers will aggregate their respective shares received from mobile devices, and then they will send their aggregate share outputs to the output receiver who can reconstruct the final aggregate metrics from the system. I also mentioned to you that we were aiming to achieve differential privacy for the output. And if you have not heard about differential privacy before, differential privacy is this notion of protecting the user that says that an output receiver cannot learn anything about my contribution to the aggregate metric, even if they know the inputs of all the other users in the system. So, and the way we achieved differential privacy in our system was by leveraging some techniques that are called amplification by aggregation. And at a high level, how these techniques work is that the user device will first flip each of the bits in this input vector that it has computed with some very small probability. And this probability is much smaller than what we would need if we wanted to apply local differential privacy mechanisms. But once all of these shares are aggregated by the aggregation servers, the final result will be providing differential privacy while also achieving much better utility compared with a local differential privacy solution. So these were kind of the main steps in this protocol, and let's just look back at how we were meeting the design goals that we started with. First, we were collecting only well-defined metrics that were used to answer specific questions from the health authorities. We were choosing the PRIO architecture that guaranteed that only aggregated and differentially private metrics will be released to the health authorities. And we were also guaranteeing the validity of the inputs, that nobody can skew the final output, by employing and using the zero-knowledge proofs and further also device attestation techniques. For having a system that works across millions of devices, efficiency was of tantamount importance, and that's why we chose to use this solution that relied on a single-shot protocol where all the clients contribute only once in the protocol, and also requires only one round of interactions between the servers. And of course, we managed to have a common solution that both Google and Apple agreed to implement. So now that we have an idea how this protocol works at a high level, let's look at how we instantiated and deployed this protocol. So translating this design into a deployment that works on millions of user devices that stream data all the time involved many moving parts. Of course, first we had to choose the servers that will be acting as the two non-colluding aggregators in order to kind of match the trust model for the system. Second, we had to have mechanisms in which we will enable health authorities and users to decide whether they want to join and participate in the system. We wanted to decide whether we'll do some additional attestation for the contributions that will be included in the final aggregated metrics. We wanted to decide which parties will need to be available online all the time during the execution of the protocol, and which part of the computation can be done asynchronously offline. We had to make choices about the architectures and the implementation that we will use for the system. And last but not least, we had to come up with ways that we can test and debug the system to make sure that it works as expected. So let's look at how we answered some of these questions. So first, let's see at who are the non-colluding aggregation servers that we deployed in the US. The first of these parties was the Internet Security Research Group, which is a California public benefit corporation for digital infrastructure projects. And you might have heard about ISRG also as a certificate authority. And the certificate authority that it runs is called Let's Encrypt. The second aggregation server is run by the National Cancer Institute at the National Institutes of Health, which is an agency of the US Department of Health and Human Services. So both of these parties were well known in the public sphere and were already serving for public benefit. So there was a common agreement that these two parties would meet the trust model for the underlying solution. In order to facilitate the access of health authorities to this data, we also decided to have a web portal that will provide data access and graphical representation for the aggregate and differentially private metrics that could be easily usable by the health authorities. This web portal was hosted by another party, which is called MITRE. It's a non-for-profit corporation that has been involved with the COVID-19 efforts already in many other contexts. One more party in the architecture was what we called ingestion servers. And these ingestion servers came from the desire to do some additional attestation for the contributions that were included in the aggregate metrics. In particular, we wanted to make sure that we are not receiving fake contributions from non-existing devices that might skew the final metrics. So these ingestion servers leverage device attestation techniques that each of the company offers for their respective operating system. So the ingestion servers are run by Google and Apple respectively for their devices. These ingestion servers receive only encrypted data. Each mobile device encrypts their contributions under the public keys of the two aggregation servers, and only this encrypted data goes to the ingestion server that checks the device attestation, whether this is a real device, and filters all contributions that come from non-verified devices. Another kind of goal for this ingestion server is to drop any metadata that comes with the contribution, which includes IP addresses or some timestamps. So this ingestion server will receive the encrypted data, it will batch contributions and then shuffle them and send them to the two aggregators. One other purpose that this ingestion server served was that it was generating the randomness that was needed for the verification, distributed verification of the zero-knowledge proofs for the validity of the inputs. So in particular, these ingestion servers were generating the random points for the polynomial identity tests that were involved in these zero-knowledge proofs. So thus our system consisted of these three stages, which was the data collection that kind of sends all the encrypted data to the ingestion servers, that process the data as we just discussed, then the data aggregation phase, which involves the two aggregation servers processing the zero-knowledge proofs and then aggregating the corresponding data, and then writing every 8 hours their local aggregates to the MITRE party that was aggregating what it had received from the two servers every 24 hours and was providing the resulting metrics in a user interface available to the health authorities that they can access anytime. So now if we want to put everything that I described up to here in one picture, we have the iOS and the Android devices that are reporting encrypted shares and proofs that go through the ingestion servers that filter based on device attestation. and then they split the contributions to send them to the 2 aggregation servers, and then the 2 aggregation servers, after doing the processing, are forwarding the final aggregates to MITRE that provides the user interface for the web portal available to the health authorities. So as I mentioned, ENPA has 2 types of consents. First, each health authority, which in this case was the corresponding state public health authorities, needs to elect to activate this private metrics system. And this is done by signing a contract with the MITRE Corporation. And then separately from that, for each state that offers the private analytics, each user has to choose whether they want to contribute to this private metrics, their data. So the current deployment of the exposure notification private analytics is running since December 2020 in 14 US states and 4 Mexican states. We're collecting 9 different metrics, and the system is processing millions of contributions daily. And as I mentioned in the beginning of the talk, there was this study coming from Washington State that estimated how many lives have been saved and how many infections have been prevented thanks to the exposure notification system, which was kind of a gratifying use of the data that we managed to collect with this privacy-preserving system. If you want to learn more about the actual protocols that we implemented in our system, you can look at our white paper. So finally, I just want to make a few points about the practical sides of this deployment. It's hard to overstate how important it is to have a solution that is easy to use and understand. We were interacting with these health authorities that were already overwhelmed with the COVID-19 response, and they had very limited availability to kind of interact and engage with us. But we needed to have a very convincing way to explain to them the privacy and security properties. And similarly, we needed to have a way to interact with the users and convey to them what are the guarantees of the system. So for future work, I think standardization of some of these advanced techniques and also education on users and participating parties will be very important. Another major challenge in the system was bootstrapping trust between different participants that didn't have established channels to share identity or secrets. And while this was fairly easy, when we were talking about the 2 aggregation servers, the biggest challenge was how we will do the distribution of the encryption keys to the mobile devices. Initially, we wanted to use TLS certificates, which is a common way to distribute key material to mobile devices. But what it turned out is that the Certificate Authority Browser Forum baseline requirements are very narrowly defining the allowable uses of keys that can be included in TLS certificates. And in particular, those are restricted only to web communication. And our keys were not going to be used for web communication, but rather for bootstrapping trust in these multi-party computation protocols. Thus, certificate authorities were hesitant to issue such certificates because they could be revoked as certificate authorities. So what we ended up using was a dedicated Apple certificate authority, which was going to be trusted only in the context of the ENPA system, but would not be generally trusted for web communication. Our solution is running the 2 aggregators on 2 different cloud providers to maximally meet the requirements of non-colluding parties. And in particular, one of the aggregators is running on AWS, and one of them is running on GCP. So as part of this, we needed to figure out how we can give workloads that are running on one cloud access to workloads on the other cloud. So we had to deal with many issues for identity federation across AWS and GCP. And this is something that is definitely very interesting for future work, because it was very nice that this was possible at all. But I think if such kind of distributed systems running on different clouds will be something upcoming in the future, maybe better identity federation tools will be very useful across these cloud providers. Last but not least, there was the question of how do we test and debug this system. A system that by design makes all of its intermediate states unintelligible, right? These multi-party computation techniques aim to hide everything in the intermediate states except the output. For this also to simulate anything that's happening in the system, we needed to find devices that simulate an exposure, then go through the ingestion server, then through the aggregation servers, and then at the end we had to deal also with the fact that we have differential privacy, so we could not even necessarily predict what the exact output is. So we ended up having some custom builds that were disabling some of the privacy features in order to do the testing and debugging. And I think for the future, coming up with a principal approach for functional verification, alerting, and observability for this type of solutions will be a big open problem. So in conclusion, I would like to say that private analytics is a solution that allowed health authorities to evaluate the effectiveness of the exposure notification system, and it deployed a privacy-preserving solution based on secure multi-party computation. To my knowledge, this is the largest deployment of such techniques in practice. This project was developed across 5 institutions and involved about 30 people. It took about 6 months to go from an idea to a deployment, and this has been running since December 2020, serving millions of people, and up to date it has processed more than 39 billion metrics coming from different devices. So I think this concludes my talk, and thank you for your attention, and I'll be happy to answer questions.